Okay, this is my second lesson on Hooke's law, which involves springs and objects, or elastic strings and objects. And Hooke's law says this, that the force required to extend or compress a spring by some distance is proportional to that distance. So a spring can be extended or compressed. If we're talking about an elastic string, it really only gets extended. If I compress it, it just becomes kind of slack. And Hooke's law says this, that the force on the string by the object is K multiplied by the extension length. The extension length is always what we call the actual length divided by the natural length. So if the string, if there's nothing, if there's no force pulling the string, that's its natural length. If there is a force pulling on the string, it can be extended here. We're not talking about inextensible strings. So the force on the string by the object is this. The force on the object by the string will be the same in magnitude but opposite in direction. So the force on the string or spring by the object is going to be downwards, but the force on the object by the spring in this case would be upwards. Okay, so we're going to have a look at a question that also involves our recent work on circular motion. So let's have a read through of this. It says an elastic string of natural length 1 meter. So there's my L0. That's my natural length, 1 meter. L0 is 1 meter. It's in meters already. I don't need to convert. Is attached at one end to a fixed point on a smooth horizontal surface. So that's important that we're dealing with a horizontal surface. Horizontal circular motion we did quite a bit of work on recently. And at the other end to a particle of mass 0.5 kilos. Okay, again, it's in kilos already, no need for conversion, which is moving in a circle at 2 radians per second. So circular motion, 2 radians per second. That's my angular velocity. That's what we would have called omega is 2. Notice no need for unit change, 2 radians per second. That's our standard units for angular velocity, so omega equals 2. If the elastic constant for the string is 6, there's my elastic constant or my spring constant, which is 6. Again, the units are newtons per meter. No need to convert to any units. Then find the radius of the circle. So we're trying to find r. So we have an object that's moving around in circles. Suppose I take a snapshot in time. It's attached at one end to a fixed point. So here's the fixed point. This is my string, and it's attached at the other end to some particle that's moving around in circles. So this point is fixed, and this particle is going to be traveling around this circle. So there's my radius length in there. And my radius length is actually going to be what we call the actual length of the string. So the actual length of the string is going to be whatever the radius of the circle is. Okay, so we're going to tie in a couple of things. Remember, Hooke's law says that the force on an object by the string is equal to K times the extension. So we take this object over here, take a snapshot of it, look at a force diagram. At the moment, there is a centripetal force acting on it. How do I know there's a centripetal force? Because it's traveling in circles. If something is traveling in circles, there must be some centripetal force making it travel in circles. So the centripetal force is going to equal to K times the extension. And we know that the centripetal force is always m or omega squared. Again, that's work we've looked at in previous classes. So we have an equation here. I'm just going to substitute in everything I know and then solve it. So K is the elastic constant, which in this case is 6. The extension is the difference between the actual length, which is the radius of the circle, and the natural length, which in this case is 1. So it's going to be r subtract 1. And that's going to give me the mass times the radius times omega squared. Mass I know is 0.5. Times the radius, or times omega squared. Omega is given, that's 2 radians per second, so it's 2 squared. And now all I have to do is solve this linear equation. 6 times r minus 1, well that's 6r subtract 6. And that's equals a half times 4r, that's equal to 2r. Okay, I'm going to subtract 2 from each side. I'm going to add 6 to both sides. So I'm going to get 4r equals 6. And now I'm going to divide on both sides by 4 and simplify the fraction. So 6 over 4, 3 over 2, or 1.5. That's going to be the radius of the circle. Radius 1.5 meters. So that is the radius of the circle. Okay, so that's the radius of the circle. The centripetal force here, this value for F is going to be equal to m or omega squared. So that's going to be, F is going to equal to mass half times 1.5 times 2 squared, which works out as 3, I think, newtons. So the strain is exerting a force of 3 newtons on the object at all times. Remember, that's a magnitude of the force is 3 newtons. The direction of the force, well, it's a centripetal force. It's always towards the center of the circle. So at the moment that the particle is up here, the centripetal force will be acting in that direction. When it's down here, the centripetal force will be acting in that direction. As it moves around, the direction of the centripetal force will change, but the magnitude is always going to be 3 newtons. The radius of this circle, 1.5 meters. The extension length is the difference between the actual length and the natural length, or minus 1, so 0.5 meter. So the string is extended 0.5 meter, centripetal force 3 newtons, radius of the circle 1.5 meters. Okay? Hooke's law combined with circular motion. You got to know it all. Practice, practice.